Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi Herman and Corin. So we have chatted about redundancy and preparedness in a number of episodes, and there's one thing that we mention frequently in the context of high stakes redundancy, if you will, that kind of 99.999% availability requirement, or just in the context of government continuity of operations, especially C2 military backbones and stuff like that. We frequently mention that redundancy has to be like redundant everything, because we're used to thinking about it just in terms of redundant power, redundant internet, and we actually did an episode about that way back, talking about what this actually means in practice at a government level. When you don't just need redundant communications, you need redundancy of leadership. And what I'd like to do in today's episode is talk about some of the fundamental blocks of redundancy in this context of data centers, command centers, whatever else is a high critical asset. Now, this could be applicable to the home user or a small business user. There's nothing stopping anyone from taking a cue from government, but I think it's fair to say that there's a pretty low cutoff at what point you're going to just be wasting time and money. One thing that I've done for years and highly recommend, and it's just because I lived with catastrophically bad internet for so long, is redundant internet. It's basically having a second WAN, second wide area network. It's 4G is one of the few things here in Israel that's relatively cheap. So in addition to our fiber optic, I have a 4G internet line, and that can flip over to it if it goes down, and a UPS, and that's where I draw the line as to how much I care about this stuff. But if you're doing it at a more significant level of scale, they do put in some crazy things. We talked about redundancy in the context of the military's even developed some electro-pulse communication systems that can survive that. But let's take a slightly more pedestrian use case, whether we're talking about maybe a dispatch center or a hospital. At a minimum, they're going to have multiple redundant communications. They're going to have redundant power supply. They might have also redundant HVAC. And that's what I'd love to get into in today's episode. There is a point for redundancy, and I'd be interested to know your thoughts on where that hits and how they calculate it, by which point the returns are diminishing. So if I have, let's take my internet connection example where I've got two internet providers. Now I could go out tomorrow and buy another mobile router for another mobile network, and then I could have Starlink, and now I'm at 4. Now I would say at 4 there's no point adding a fifth, and I'd probably say I wasn't pretty sure there was no point even adding the fourth layer of redundancy. So how do they figure out where that point is, at which point there's enough? Because you can keep going down and down and down, and all you end up with is a massive networking cabinet with a Starlink connection that will only ever be used if the fiber optic line, 2 cellular networks are down, then we go to that, right? So that doesn't seem like a sensible use of resources. And then regarding power, I guess there's a main electricity grid, there's generators. What are those systems? Is that kind of the typical setup? And finally, we talked about HVAC, which I know is something that people think about, and out of my ballpark a bit, but for those who are in this world, it's clearly something that is integral. So that's the systems I know about. Anything else I'm missing? And how is this done? I mean, it's a really fascinating world to think about, and there's probably more facilities with amazing redundancy around us than we actually know about. But even at those basic ingredients, how is it actually done in practice? Herman and Corin, over to you.
Welcome back to my weird prompts. I am Korn, and I am sitting here in our living room in Jerusalem with my brother Herman, who I am reasonably certain has a backup plan for when his backup plan's backup plan inevitably fails.
Herman Poppleberry at your service, Corn, and you are not wrong to be suspicious. If the main light bulb in this room burns out, I have a flashlight in my pocket, a candle under the coffee table, and a headlamp stashed inside that hollowed-out book on the shelf. It is just basic common sense, really. You cannot rely on a single point of failure in a world governed by entropy.
Basic common sense for you, maybe? For the rest of us, it is just a lot of extra stuff to trip over in the dark. But today's prompt from Daniel is right up your alley, Herman. He wants to talk about redundancy, specifically in high-criticality facilities like hospitals, military command centers, and Tier 4 data centers. He's asking about the fundamental blocks of these systems and, more importantly, where the point of diminishing returns is. At what point does adding more safety just become a waste of money?
This is a fantastic topic, and quite timely given the global strain on infrastructure we have seen over the last couple of years. We have touched on redundancy before, but usually in a more casual home user sense, like having 2 external hard drives for your photos. Daniel is pushing us into the deep end here. We are talking about the difference between a $5 flashlight and a $50 million backup power system designed to survive a direct lightning strike or a coordinated cyber attack.
Right, and it is interesting because we often think of redundancy as just having a spare tire in the trunk. But in these high-stakes environments, it is about maintaining continuity of operations under extreme stress. It is not just about having a second thing. It is about the seamless transition. How does that second thing take over without the equipment even realizing the first one failed?
Exactly. In the industry, we often talk about the nines. 99.9% uptime, which sounds great, but that actually allows for nearly 9 hours of downtime a year. If you are a hospital, 9 hours of no power is a massacre. So they aim for 5 nines, 99.999%. That is less than 6 minutes of downtime per year. Those extra nines are where the real engineering and the real money lives.
So let us start with the basics. Daniel mentioned power, internet, and HVAC. If we are looking at a hospital or a military command center, what does redundant power actually look like beyond just a big battery in the basement?
The first layer is the uninterruptible power supply, or UPS. But in a high criticality facility, the UPS is not meant to run the building for hours. Its job is to bridge the gap, the black start time, between the grid failing and the generators kicking in. It handles that split second of darkness that would otherwise crash every computer, ventilator, and life support machine in the building. In a modern facility, these are often massive flywheels or lithium-ion arrays that can discharge a massive amount of energy instantly.
And those generators are not just your typical backyard models you buy at the hardware store.
No, not at all. We are talking about massive diesel or natural gas engines the size of semi-trucks. In a Tier 4 data center, for example, you do not just have one backup generator, you have what is called N+1 or even 2N redundancy. If the facility needs 10 megawatts to run, you might have 12 generators, each capable of 1 megawatt. That way, 2 can fail or be down for maintenance, and you are still fine. That is N+2. But in a 2N system, you have 2 completely independent power plants. If one entire side of the building explodes, the other side carries the full load.
But Daniel brought up an interesting point about the fuel. If the grid is down for a week, those generators need a lot of diesel. You cannot just call the local gas station and ask for a fill-up during a national emergency.
That is where the logistics of redundancy come in. These facilities often have massive underground fuel tanks that can keep them running for 72 hours or even a full week at full load. And they have priority contracts with fuel delivery companies. In a crisis, the fuel truck goes to the hospital or the command center before it goes anywhere else. Some facilities even have dual fuel generators that can run on diesel or natural gas, giving them another layer of protection if the gas lines are cut or the diesel supply chain breaks down.
It is like a hierarchy of survival. But I want to push on the power thing for a second. What about the path the power takes? If you have 2 generators, but they both plug into the same switchboard, and that switchboard catches fire, You are still in the dark.
You have hit on the concept of path diversity, corn. That is a huge part of the fundamental blocks. In a truly redundant system, you have two completely separate paths for the power to travel. We call this an A and B power feed. You have two different utility feeds coming from two different substations, two different sets of switchgear, and two different sets of wiring all the way to the equipment. If you look at high-end servers or medical imaging machines, they actually have two power plugs. One goes to the A side and one goes to the B side. If any single component along either path fails, a breaker trips, a wire melts, a transformer blows, the equipment keeps humming along on the other one.
That seems like a lot of copper and a lot of money. You are essentially building two of everything.
It is. It more than doubles the cost of the electrical infrastructure because you also have to pay for the space to house it and the people to maintain it. And this leads us directly into Daniel's question about diminishing returns. If you have an A and B feed, you are protected against almost any single point of failure. But what if you want a C feed? Now you are tripling the cost for a marginal increase in reliability. Most organizations stop at 2 because the probability of both independent paths failing simultaneously is statistically negligible, unless it is a catastrophic event that would destroy the building anyway.
Okay, so that is power. Let us talk about connectivity. Daniel mentioned his own setup with a second wide area network and a 4G backup. But for a command center or a global data center, I imagine it is more than just a different SIM card.
Connectivity redundancy is fascinating because it is so easy to get wrong. Many companies think they are redundant because they buy internet from two different providers, say provider A and provider B. But if both of those providers are leasing space on the same physical fiber optic cable that runs under the bridge down the street, and a truck hits that bridge, both connections go dark. This is what we call a fate-sharing failure.
So you need physical path diversity as well as provider diversity.
Precisely. You want one fiber line coming in from the north side of the building and another coming in from the south. You want them to terminate in different meet-me rooms within the facility. Or better yet, one fiber line and one high-speed microwave link on the roof. Or now, as Daniel mentioned, a Starlink terminal. The idea is to have completely different physical mediums. If the fiber gets cut by a backhoe, which is the #1 killer of the internet, by the way, the satellite still works. If a massive storm knocks out the satellite, the fiber is still there.
I remember reading about how some military backbones use something called BGP, or Border Gateway Protocol, to handle this automatically. How does that work in practice?
BGP is the glue of the internet. It allows the network to automatically reroute traffic if one path becomes unavailable. In a high-stakes environment, you want that transition to be so fast that a voice-over IP call does not even drop. You might hear a tiny click, and that is it. For a command center, they might also use anycast routing, where multiple locations around the world all share the same IP address. If one data center is nuked or goes offline, the rest of the internet just automatically sends the data to the next closest one.
Let us move to something that people often overlook, but Daniel specifically mentioned, HVAC, heating, ventilation, and air conditioning. Why is that considered a critical redundancy block? I mean, if the AC goes out in a hospital, people just get a bit sweaty, right? It is uncomfortable, but is it critical?
In a hospital, it is actually a matter of life and death. Operating rooms need precise temperature and humidity control to prevent infection and keep equipment calibrated. But in a data center, if the cooling stops, the equipment will literally melt or shut itself down within minutes. Modern AI servers, like those using H100 or B200 chips, generate an incredible amount of heat. Without constant airflow and chilled water, they reach critical temperatures faster than you would think.
So you need redundant chillers.
You need redundant everything. Redundant chillers, redundant pumps, redundant cooling towers, and redundant air handlers. And just like the power, you want them on different circuits. There is also the concept of a thermal flywheel. Some facilities use massive tanks of chilled water that can keep the building cool for 30 minutes or an hour even if the chillers fail, giving the engineers time to fix the problem or the backup systems to engage. If you lose cooling in a high-density data center, you have about 90 seconds before things start failing.
It is interesting how all these systems are interconnected. You need power for the HVAC, and you need HVAC to keep the power electronics from overheating. It is a big, complex web where a failure in one can cascade into another.
It is a feedback loop. And that brings us to the more exotic stuff Daniel mentioned, like electropulse survival or EMP hardening. This is where we move from standard high criticality into the realm of national security and doomsday engineering.
Right, an electromagnetic pulse from a high-altitude nuclear blast or a massive solar flare could, in theory, fry almost any unprotected electronic device by inducing a massive current in the circuits. How do you even build redundancy for that?
It is less about redundancy and more about hardening. You build what is called a Faraday cage. The entire room or even the entire building is wrapped in a continuous shield of conductive material like copper or steel. Every wire that enters the building power, data, even water pipes has to go through a specialized surge protector or a waveguide that can react in nanoseconds to block the pulse.
That sounds incredibly expensive. Is that something a standard hospital would do?
Generally, no. The cost of EMP hardening a standard hospital would be astronomical. It is usually reserved for things like nuclear command and control centers, certain government bunkers, and some very high-end telecommunications hubs. For a hospital, the risk of an EMP is considered so low compared to the cost of protection that it falls into that category of diminishing returns. They focus on more likely threats like hurricanes or cyber attacks.
Which brings us to the core of Daniel's question. How do organizations determine that point? How do they decide that 2 generators are enough, but 3 is a waste of money?
It usually comes down to a formal risk assessment called a failure modes and effects analysis, or FMEA. You look at 2 things, the probability of a failure and the impact of that failure. If you are a small business and your internet goes down for an hour, the impact is low. You lose some productivity, maybe a few sales. So, you spend $100 on a backup router.
But if you are a Tier 1 trauma center and the power goes out during 10 simultaneous surgeries, the impact is catastrophic. People die.
Exactly. When the impact is human life or national security, the acceptable probability of failure drops to almost 0. That is when you start spending millions on those extra 9s. But even then, there is a curve. The first 90% of reliability is relatively cheap. The next 9% is expensive. The next 0.9% is very expensive.
I have heard this called the rule of 9s. Each extra 9 after the decimal point usually costs 10 times more than the one before it.
That is a very good rule of thumb. If it costs $1 million to get to 3 9s, which is about 9 hours of downtime a year, it might cost $10 million to get to 4 9s, which is about 50 minutes a year. To get to 5 9s, which is less than 6 minutes of downtime per year, you are looking at $100 million. At some point, the money could be better spent elsewhere.
Right. If a hospital spends $50 million to get from 4 9s to 5 9s, they might be able to save more lives by using that money to buy 10 new MRI machines or hire 50 more nurses. It is an ethical and financial calculation.
That is the trade-off. Engineers love to build perfect systems, but administrators have to live in the real world of budgets. There is also the risk of over-engineering. This is something I find fascinating. The idea that adding more redundancy can actually make a system less reliable.
Wait, how does that work? Is it not always better to have a backup?
Not necessarily. Every time you add a redundant component, you are adding complexity. You are adding more wires, more sensors, and more software to manage the failover. If the transfer switch, the system that is supposed to switch from the main power to the backup power, fails, it does not matter how good your generator is. You have created a new single point of failure.
I think I see what you mean. It is like having 2 steering wheels in a car. If they're not perfectly synchronized, they might fight each other and cause a crash that would not have happened with just one.
That is a perfect analogy. In the world of complex systems, we call this interactive complexity. Sometimes the redundant systems interact in ways the designers did not anticipate, leading to what the sociologist Charles Perrow called a normal accident. The very thing you built to prevent a disaster actually causes it because the system became too complex for a human to understand in a crisis.
So, the goal is not just more redundancy, but smart redundancy, keeping it as simple as possible while still covering the most likely and most impactful failure modes.
Right? And Daniel mentioned something else that I think is the most overlooked part of this whole equation: leadership and human redundancy.
Continuity of leadership. We have talked about this in the context of government, like the designated survivor during the State of the Union address.
It applies to any high criticality facility. If you have a hospital with the best redundant power in the world, but the only person who knows how to manually start the generators is on vacation and cannot be reached, your redundancy is useless. You need redundant knowledge. You need clear protocols that multiple people know how to execute. We call this the bus factor. How many people can be hit by a bus before the organization stops functioning?
It is the human element. You can have all the copper and diesel in the world, but if the people in charge cannot communicate or make decisions, the system fails.
This is why organizations like the military or large hospitals do drills. They practice for the day the grid goes down. They find the gaps in their procedures. They realize that, oh, the backup radio works, but we forgot to charge the batteries for the handheld units. Or the backup command center is great, but it takes 2 hours to drive there in traffic.
It is about building a culture of preparedness, not just a list of hardware. I am curious about the practical implementation. If you were designing a new command center today, Herman, where would you start?
I would start with the geography. You do not want your redundant facility to be in the same floodplain or on the same fault line as your primary facility. If a hurricane hits the city and both your data centers are in that city, your redundancy might be wiped out in one go. We call this geographic diversity.
That is why companies have data centers in different states or even different continents.
Exactly. Then I would look at the utility feeds. I would want power and water coming from different sources. I would build in layers. Layer 1 is the immediate failover, the UPS, and the redundant network paths. Layer 2 is the long-term sustainment, the generators and the fuel supplies. And Layer 3 is the recovery, the off-site backups, and the alternate leadership locations.
And how would you decide when to stop? When do you say, okay, we are not going to spend the money on the EMP shield?
I would use that FMEA tool I mentioned. You list every possible thing that could go wrong, from a squirrel chewing through a wire to a nuclear strike. You assign a score to how likely it is and another score to how bad it would be. Then you multiply them. The highest scores get the most investment.
So, if the squirrel is very likely but the impact is low, it gets a moderate score. If the nuclear strike is very unlikely but the impact is total, it also gets a moderate score. But if a local power outage is very likely and the impact is high, that is where you put your money first.
Precisely. It is a rational way to navigate the diminishing returns. You address the biggest risks first, and you only move down the list as far as your budget allows. For most organizations, that means they never get to the EMP shield, and that is okay. It is a calculated risk. You have to accept that you cannot protect against everything.
It is interesting to think about how this applies to us as individuals, too. Daniel mentioned his 4G backup. I have a second set of keys to the house. It is the same logic, just on a different scale.
It really is. The fundamental blocks are the same: power, communication, and a plan. For us, it might be a portable power bank and a paper map in the car. For a hospital, it is a 10 megawatt generator and a satellite link. The goal is the same: to reduce the probability that a single failure can ruin your day or your life.
I think one of the most practical takeaways for anyone listening, whether they are running a data center or just their own household, is to identify your single points of failure. What is the one thing that, if it breaks, everything stops?
That is the most important question. Is it your internet? Is it your phone? Is it your car? Once you identify it, you can start thinking about a cost-effective way to add a second path. It does not have to be expensive. Sometimes redundancy is just having the phone number of a neighbor who has a spare key, or keeping a $20 bill hidden in your phone case for when the credit card machines go down.
Or having a brother who keeps a flashlight in his pocket.
Exactly. Never underestimate the redundancy of a well-prepared sibling.
We have covered a lot of ground here, from diesel generators to Faraday cages. It is a reminder that the world we live in, especially the high-tech parts of it, is held together by these invisible layers of backup systems. It is easy to take for granted that the lights will stay on and the internet will work, but there is a massive amount of engineering preventing that from failing.
It is a testament to human ingenuity and, frankly, our collective anxiety about things breaking. We have built this incredibly resilient infrastructure because we know that eventually something will go wrong. The universe is messy, and redundancy is our way of shouting back at the chaos.
And that is the heart of it. Redundancy is not about being pessimistic. It is about being realistic. It is acknowledging that failure is a part of any complex system and planning accordingly. It is about resilience.
Well said, Korn. I think we've given Daniel a good deep dive into his prompt. It is a fascinating world, and the deeper you go, the more you realize how much thought goes into keeping the lights on. It is not just about the machines, it is about the foresight.
Definitely. And before we wrap up, I want to say that if you are enjoying these deep dives into the weird and wonderful prompts Daniel sends our way, we would really appreciate it if you could leave us a review on your podcast app. It helps other people find the show and lets us know what you think.
It really does make a difference. We love seeing those reviews pop up. It is like a little hit of dopamine for the prepared mind.
You can find My Weird Prompts on Spotify, Apple Podcasts, or wherever you get your podcasts. We are also at myweirdprompts.com, where you can find our full archive and a contact form if you want to reach out.
And you can always email the show at show@myweirdprompts.com. We would love to hear your thoughts on redundancy or any other weird topics on your mind. Maybe tell us about your own backup plans.
Thanks for listening to My Weird Prompts. I am Korn.
And I am Herman Puppleberry.
We will see you next time. Goodbye.
Stay prepared, everyone. Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.